How ballistic missiles work. Ballistic missiles represent one of the most sophisticated and strategically significant weapons systems in modern military arsenals. These powerful projectiles follow a ballistic trajectory, a curved path, determined primarily by gravity and aerodynamic forces after an initial powered flight phase. Unlike cruise missiles that maintain powered flight throughout their journey, ballistic missiles rely on the fundamental principles of physics established centuries ago by Sir Isaac Newton, combined with cutting-edge aerospace engineering and precision guidance systems. The development of ballistic missiles revolutionized warfare and geopolitics in the 20th century, fundamentally altering military strategy and international relations. From their origins in World War II, German V-2 rockets, to today's intercontinental ballistic missiles capable of delivering nuclear warheads across continents. These weapons have become central to national defense strategies and nuclear deterrence policies worldwide. Understanding how ballistic missiles function requires examining their complex interplay of propulsion systems, guidance mechanisms, structural engineering, and physics principles that enable them to accurately deliver payloads across vast distances with remarkable precision. Basic principles of ballistic flight. The fundamental concept underlying ballistic missile operation is ballistic trajectory. The path an object follows when it is launched into the air and subsequently moves under the influence of gravity and air resistance. Once the powered phase of flight ends, a ballistic missile becomes essentially a projectile, following the same physical laws that govern any thrown object, albeit at much higher speeds and altitudes. The trajectory of a ballistic missile consists of three distinct phases. The boost phase occurs during powered flight, when the missile's propulsion system accelerates it to the required velocity and altitude. During this phase, which typically lasts several minutes, the missile can still be maneuvered and is most vulnerable to interception. The mid-course phase follows, during which the missile or its warhead travels through space in a ballistic arc, reaching altitudes that can exceed 1,000 kilometers for intercontinental missiles. Finally, the terminal phase begins when the warhead re-enters the atmosphere and descends toward its target. The mathematics governing ballistic flight are rooted in classical mechanics. The range of a ballistic missile depends on its launch angle and initial velocity, with the optimal angle for maximum range being 45 degrees in a vacuum. However, real-world factors such as atmospheric drag, Earth's rotation, and gravitational variations complicate these calculations significantly. Modern ballistic missiles must account for these variables through sophisticated computer models and guidance systems. Propulsion systems. The heart of any ballistic missile is its propulsion system, which must generate enormous thrust to accelerate the missile to velocities often exceeding 7 kilometers per second. Most ballistic missiles employ multi-stage rocket designs, where each stage burns its fuel and is then jettisoned to reduce the missile's mass for subsequent acceleration. Solid propellant rockets are commonly used in ballistic missiles due to their reliability, long storage life, and rapid deployment capability. These systems use a solid fuel mixture containing an oxidizer, typically ammonium perchlorate, combined with a fuel such as aluminium powder and a polymer binder. The solid propellant is cast into the rocket motor casing in a specific grain pattern that controls the burn rate and thrust profile. Once ignited, solid rocket motors cannot be shut down or restarted, making them simple but inflexible. Liquid propellant systems, while more complex, offer greater performance and control flexibility. These systems typically use combinations such as liquid oxygen and kerosene, or more exotic hypergolic fuels that ignite spontaneously when mixed. Liquid rocket engines can be throttled, shut down, and restarted, providing greater mission flexibility. However, they require more complex fuel handling systems and longer preparation times. The propulsion system must not only provide sufficient thrust, but also maintain stable flight during the boost phase. This requires precise thrust vector control. It's often achieved through gimbal-mounted engines or aerodynamic control surfaces that can redirect the exhaust flow to maintain the desired trajectory. Guidance and navigation systems. Modern ballistic missiles use advanced guidance systems that blend multiple technologies to ensure precise targeting over long distances. These systems must perform flawlessly during intense launch acceleration. In the vacuum of space, and during high-speed atmospheric re-entry. Their ability to maintain accuracy across thousands of kilometers is critical to mission success. Inertial guidance systems are the core of missile navigation, relying on accelerometers and gyroscopes to track acceleration and orientation. Advanced models use ring laser or fiber optic gyroscopes to detect tiny shifts in position, enabling high precision. These systems operate independently, using dead reckoning to calculate the missile's location and velocity in real time. To enhance accuracy, many systems integrate GPS updates during flight, though these can be jammed or disrupted. Some missiles also include stellar navigation, using star patterns for additional position fixes. The guidance computer must constantly adjust the missile's trajectory, factoring in wind, gravity variations, and atmospheric conditions using fast processors and complex algorithms. Warhead and payload systems. Ballistic missile payloads vary by mission, with nuclear warheads remaining the most strategic due to their massive destructive power, ranging from kilotons to megatons. These warheads must endure extreme acceleration, space conditions, and the heat of re-entry. Conventional warheads use high explosives for blast, fragmentation, or effects like electromagnetic pulse generation. Some missiles carry multiple independently targetable re-entry vehicles to strike several targets or bypass missile defenses. The re-entry vehicle is a key engineering feat, protecting the warhead as it re-enters Earth's atmosphere at over 20 times the speed of sound. Ablative heat shields withstand temperatures near to 0 degrees Celsius, ensuring warhead survival. Structural design and materials. Ballistic missiles must endure extreme forces during launch, spaceflight, and re-entry, all while remaining lightweight to maximize range and payload. Their structural design must handle intense acceleration, temperature changes, and mechanical stress, demanding a balance between durability and weight for optimal performance throughout the missile's entire flight path. Advanced materials like high-strength aluminum alloys, titanium, and composites are essential for constructing lightweight yet strong airframes. These structures must house propulsion, guidance, and payload systems while maintaining balance and aerodynamic stability. Precision manufacturing is vital, as minor flaws can cause major trajectory errors, prompting rigorous quality control far beyond commercial aerospace standards. Defense and countermeasures. The development of ballistic missiles has driven corresponding advances in missile defense systems, creating an ongoing technological competition between offensive and defensive capabilities. Modern ballistic missiles incorporate various countermeasures designed to penetrate or confuse defensive systems. Penetration aids include decoy warheads that mimic the radar signature of real weapons, chaff dispensers that create false targets, and maneuvering re-entry vehicles that can change course to avoid interception. Some advanced systems employ hypersonic boost glide vehicles that can maneuver throughout their flight path, making interception extremely difficult with current defense technologies. Missile defense systems typically attempt to intercept ballistic missiles during their most vulnerable boost phase or during the more predictable mid-course phase. Terminal phase interception, while technically possible, is extremely challenging due to the high speeds and short engagement times involved. Conclusion: ballistic missiles combine advanced physics, precision engineering, and high technology into powerful weapons of strategic value. Their effectiveness relies on integrating propulsion systems that achieve extreme velocities, guidance systems that ensure accuracy over vast distances, and structural designs capable of surviving the harsh conditions of space and atmospheric re-entry. Though based on classical physics, ballistic missile operation requires cutting-edge application of thermodynamics, aerodynamics, and trajectory optimization. These systems must be both technologically advanced and strategically reliable. As missile defense improves, missile designs adapt with countermeasures and upgrades, highlighting their evolving role in global security and their impact on modern military strategy.